In today's lesson, we are going to be looking at exponent laws. We're going to be continuing on with our previous lesson. So the previous lesson looked at multiplying powers, dividing powers, and power of a power. We're going to look at two other examples in this lesson. So just as a warm-up, let's continue going through and evaluating each power and see what we get. So 2 to the power of 3, we get 8. 2 to the power of 2 is 4, 2 to the power of 1 is 2, 2 to the power of 0 is 1. Right, let's go through and do the same thing with the next one. 3 to the power of 4 is 81. 3 to the power of 3 is 27. 3 to the power of 2 is 9. 3 to the power of 1 is 3. And 3 to the power of 0 is 1. 5 to the power of 4, 625. 5 to the power of 3 is 125. 5 to the power of 2 is 25. 5 to the power of 1 is 5. And 5 to the power of 0 is 1. Do we see a pattern here? Do we see a pattern as we go down, or as our power or exponent decreases by 1? Do we see anything that's happening here? Well, if we go through, this is decreasing by a half, dividing by 2, dividing by 2, dividing by 2. This one's dividing by 3 every time. This one's dividing by 5 every time. So we do kind of see a pattern there, and it kind of relates to the ratio or our exponential function that we've talked about before. And using this pattern, we can go through and we can figure out what anything or a base to the power of 0 is. Because is this pattern going to change for a different base? Well, yes, it will be a different decrease, right? If I had 6 to the power of 4 and then 6 to the power of 3, I'd be decreasing or dividing by 6 every time. Or if it was 100 to the power of 4, then 100 to the power of 3. I'm dividing by 100 every time. But regardless of what base I have, I'm still going to have a similar thing or similar pattern, and I should get these values at the end. So it doesn't matter what my base is. Anytime I reverse that pattern or reduce it, or reduce the power or the exponent down to 0, I should get that it equals 1. So that's one of the rules that we're looking at, is that anything to the power of 0, let me use a different color here, anything to the power of 0 is equal to 1. Now, let's take those patterns that we just looked at, and let's continue them, except let's go into the negatives. So if I decrease by 1 again, from 0 to -1, what would the pattern continue? I was at 1. The pattern says I'm dividing by 2, so 1 divided by 2 is a half. And if we continue that, what's 1/2 divided by 2? Well, that's a quarter. What's 1/4 divided by 2? That's an eighth. And what about an eighth divided by 2? Well, that's a 16th. 1 over 16. What would the pattern be for 3 if we're reducing 3 every time? Well, I start at 1. The pattern says I'm dividing by 3, so 1 divided by 3 is a third. What's a third divided by 3? Well, a third divided by 3 is a ninth. And we can see what the pattern's going to do. It's going to keep on dividing by 3. So a third, a ninth, 1/27th, and 1/81st. What about with 5? Different base. Is this going to change? Or is our pattern going to change? Nope, our pattern's going to stay the same. So we were at 1. We go down one more, we're going to divide by 5. So 1 divided by 5 is a fifth. And we're going to continue that pattern as our exponent decreases by 1 every time. Divide by 5, divide by 5, divide by 5. So 1/5 divided by 5 is 1 over 25, then 1 over 125, then 1 over 625. Do we see a pattern here? Do we see a pattern going on? Right? We hopefully should see that relationship of that dividing by 5, dividing by 3, dividing by 2 every time because of what our base is decreasing, or our exponent is decreasing by. Every time we decrease by 1, we're reducing or going down by a multiple of whatever our base is. So we have 1 less 2, 1 less 3, 1 less 5. But is there any connection between the exponents, or the positive exponents, and the negative exponents? If we look at our values for 2, do we see any connection there? What about 3 and 5? Now there is a connection. So how do the values of 2 to the power of 4 and 2 to the power of negative 4 relate? Well, 2 to the power of 4 is 16. 2 to the power of negative 4 was 1 over 16. 2 to the power of 3 to the power of 2 was 9. 3 to the power of negative 2 was 1 over 9. Four to the power of 1 was 4. 4 to the power of negative 1, well, we don't have that one, but it would be 1 over 4. So hopefully now it's a little bit easier to see a connection. So how could we easily determine the value of any base to the power of a negative exponent? Well, it becomes a reciprocal. So a to the power of negative n would become 1 over a to the power of positive n, which we see which we've seen in all of our previous examples. Well, what do you think would happen if we had a fraction as a base instead? 1 over 2 to the power of 4. Well, let's check. We'll do that quickly on our calculator. 1 over 2 to the power of 4 is 1 over 16. And what about 1 over 2 to the power of negative 4? Well, this would be 16. 1 over 3 to the power of 2 is 1 over 9. And 1 over 3 to the power of negative 2 is just 9. Let's change these colors. So what do we see that's going on between here? Well, here we see the same thing. So it doesn't matter if our base is a fraction. So if I had a over b to the power of negative n, if I want to figure out what that is, I can just switch or flip my fraction, b over a to the power of positive n. And I know how to use positive exponents. That's exactly what we've been doing all along. Right? So regardless of what we have, if we have a negative exponent, we can switch or flip our base and turn our exponent to a positive. And then that will give us a power that we can work with. So that is the negative exponent law. So if we have a negative exponent, if our base is a whole number, we just flip it over 1 or put it over 1, and the reason, or under 1, and the reason being is because any whole number as a fraction is always going to be over 1. So we end up flipping these, and the exponent becomes positive. If we look at a fraction base, same thing applies. We flip our fraction, so it goes from a over b to b over a, and our exponent becomes positive. So that's how we get rid of negative exponents, and we generally want to keep things with positive exponents only. The zero exponent law, so that was the first thing we kind of noticed. Basically anything to the power of 0 is going to equal 1. It doesn't matter what the base is, it's going to equal 1. Now, the one restriction or condition is that a cannot be 0. Right? Because if a was 0, then that would mean 0 times, or 0 equals 1, which doesn't work. So the only situation where this won't work is when a equals 0. So let's go through and write each as a single positive power. So this is going to be combining some of our laws that we've looked at previously and the idea of negative exponents. So here let's simplify the top and bottom separately. Right, power of a power law, it says we multiply, so 4 to the power of 6 divided by 4 to the power of 12, because we add the exponents on the bottom. This then becomes division or subtraction, so I get 4 to the power of negative 6, 6 minus 12. Now I want to turn it into a positive power, or positive exponent, so I flip my base, 1 over 4, and the 6 becomes a positive. So 1 over 4 to the power of 6. So again, this is simplified. And then if for some reason we are asked to evaluate, that's finding the actual answer. So we get 1 over 4096. And generally speaking, we would probably be asked to evaluate as a fraction. So we want our final answer in a fraction. So we're not going to type into our calculator 1 divided by 4 to the power of 6 and get a large decimal number. Right, we don't want 2.44 times 10 to the power of negative 4, which is what my calculator gives, which is the same as saying 1, 2, 3, 4. It's much easier to work with the fraction. So generally speaking, we'll be asked to find it as a fraction. So this is the evaluated form, and we'll say leave as a fraction. Next example, so we have x to the power of negative 5 divided by x to the power of 3, all to the power of 2. So we want to start with our overall exponent first, so this power of 2. This gets applied to both parts. It's a power of a power, so that means we multiply. So this becomes x to the power of negative 10 divided by x to the power of 6. Now again, now we're dividing powers. The rule for dividing powers is we subtract. So x to the power of negative 10 minus 6 is negative 16. So now this is simplified to a single power with a negative exponent. We want to get it to a positive exponent. So even if it's a variable and not a number, we still flip it over 1, and that exponent becomes positive. So we have our simplified with a negative exponent, and then we have our simplified with a positive exponent. So again, depending on what the question asks, there might be different answers or different ways you display the answer. Next, same idea, we're going to go through and simplify this. Let's work on some of our previous laws first before dealing with the negatives. So we're not going to worry about changing anything with the negatives until we get it down to a single power. So don't worry about the negatives the way they are now. We'll just go through our normal simplifying and then worry about the negatives at the end. So in this case, for the first one, we have a power of a power. So we multiply, so we have m to the power of negative 6. This is then multiplied by another power of a power, which we get m to the power of negative 4 times negative 3, which is 12. Now we have a power times a power, which is different than a power of a power. Power times a power means we add, so negative 6 plus 12, we get m equals 6. So this one worked out nicely. We didn't have to convert to a positive exponent because our first simplified answer was already in a positive exponent. Next, again, we're just getting more complex, more complicated. So we're going to deal with this overall exponent here. It's going to apply to everything on the inside, each individual part. So in this case, negative 3 to the power of 6 to the power of negative 3. So we multiply. 6 times negative 3 is negative 18. Now our top is simplified, but on our bottom we can't simplify it fully yet. Still have to work with this negative 3 overall. 4 times negative 3 is negative 12, times negative 3 to the power of 7 times negative 3, which is negative 21. Now I can again go back and can finish simplifying the bottom. We're multiplying powers, so we add the exponents. So negative 3 to the power of negative 33. Now we're dividing two powers, so we subtract. So negative 3 to the power of negative 18 minus negative 33. So I get negative 3 to the power of 15. Again, this is simplified. And if we needed to evaluate it, negative 3 to the power of 15, we get negative 14348,907, which is our evaluated form. One thing to keep in mind: if our base is a negative, on your calculator, you want to place brackets around the base. In some cases, if we don't put brackets around the base, the calculator does not assume that the negative is part of the base. So it'll leave the negative out front, evaluate the base, and then throw the negative on at the end. Now, in some cases that may not matter. It may not change the answer. Some cases it might. So you want to be careful and make sure you put brackets on the base or around the base if we have a negative. So again, those are just some couple of examples, just working with negative exponents. Again, in some cases we may not have to worry about them, because when we simplify to a single power, we may end up with a positive exponent. So even if you have a negative exponent in a large complex question, kind of like how we started off here, or if we started off here, do not worry about converting them to positive exponents until after we simplify. Right? So don't worry about doing any of the conversions or using the laws to convert to a positive exponent until after we simplify. Because if you do it early, then you're just dealing with fractions as bases, and it just makes it a little bit more complicated. And it's a lot easier to just work with whole negative numbers when we're working with these power laws. So again, the main idea though is understanding our couple laws. One, the negative exponent law, what we do, or the rule, what we do when we have negative exponents to convert it to positive exponents, and what happens when we have an exponent of 0.